Hello and welcome to another Data Scholar Code Along. Today we're going to build a deep learning model to predict mRNA degradation. So the COVID-19 pandemic is being fought with the use of mRNA vaccines. Now, one of the biggest issues with these vaccines is that they need to be kept at a very low temperature during global distribution. And that is because the mRNA molecule is quite unstable. So what we're going to do is try and forecast the rate of deterioration, which can aid scientists and researchers in the future as they develop mRNA vaccines for other uses, such as cancer and whatnot. And this will allow them to create a vaccine that is much more stable. So what we're going to do is hopefully use a molecule degradation dataset, which is from Kaggle. And we're going to apply a deep learning model using Tensorflow and see if we can get some good predictions on whether or not a molecule will degrade. So let's jump straight to it. The first thing we're going to do is import our libraries. So let's import the data loading and manipulation libraries. We're going to import JSON, import pandas as PD, import NumPy as NP. Okay. Visualization libraries. We're going to import Plotly Express as PX. We're going to import, oh no, actually, let's just put that down a section. Deep learning libraries. We're going to import Tensorflow keras.layers because we'll use the high level API. Import Tensorflow as TF. Tensorflow as TF. And we're going from sklearn.model selection, import train test. And then let's just, for reproducibility, set seeds. So TF random set seed, and we'll call it 2023 because that's the year of this recording. We'll do the same for NumPy as well. Let's run that. Here we go. Libraries are imported. Okay, so the next part is going to import data from Okay, so what we need to do is install the Kaggle API. So we're going to do that by pip install or upgrade. I think it's upgrade because I think it may already have it, but let's just try and force a reinstall. No dependencies, Kaggle. Okay. Now what you'll need to do is have a Kaggle account and create a Kaggle key, API key, which you can download because we'll have to upload it now. So from Google Colab, import files, and then we'll want to files upload. And what we will be able to do from there is upload our Kaggle key, which is on my desktop. There it is. Okay, there we go. And now we need to make a directory. And we'll call it Kaggle. Okay. And we'll move JSON into that particular folder. We'll edit the permissions so we can actually use it. So the best one, probably 600. And okay, Kaggle.json should be fine. Okay. And now we're going to download the required dataset, which is the Stanford COVID vaccine dataset. So Kaggle competitions, download C Stanford COVID vaccine. Oh, and we're forbidden. I wonder why. I don't know what happened there. I reran the cell and it seemed to download it fine. Okay, so we've got that. Now, if we refresh this here, it's in a zip file. So what we're going to do is unzip it. And we're going to unzip it to content, Stanford COVID vaccine.zip. And we're going to put it in a directory, content data. Oh. Why can't I find that? It's right there. Let's just try copy the path. Try that. Here we go. Beautiful. So that is unzipping the contents of that folder. So let that run. Cool. Okay, so what I'm going to do is basically copy and paste the data details so we can see it into here. So let's just separate that out a little bit. It saves me typing it and explaining it. Just format that a little bit better. There we go. Columns, fine. Okay. So a number of different columns with different sort of subjects, shall we say. Got an ID column, a unique identifier of the sample. We've got the length of the sequence, the likelihood of degradation after incubating and whatnot. And our target columns here, reactivity, degradation magnesium on a pH 10, degradation magnesium on a temperature of 50 C, degradation pH 10, and degradation 50 C. Okay, so what we need to do is, let's just refresh that. It's already refreshed, and we can see we've got the train and test JSON, which has come with the Kaggle download. So we need to set them as variables. So let's train. We'll use pandas read JSON, and we'll copy the path there, and then but we'll also put lines equals true. We'll do the same for the test. Do adjustments, and then we're going to use a sample df, and that will be the sample submission. So that will be pd read csv, and we'll take that file path. Okay, and now we're going to set the target columns based on this information here. So target cols, we will bang that in a list copy these in, reactivity. We'll copy the degradation magnesium pH 10, and we'll do that for all 4. Can't even count. Okay. What's 5? It's we'll set model train to true, and you'll see why in a moment. So let's run that. There we go. Okay. So within the data, there are text formats, and what we'll have to do is change them into numerical tokens. And there are also arrays within the columns from reactivity error to degradation 50C, which we will be using as targets. Okay, so let's explore. Cool. Let's just set that to 3. Okay. So train head, just do it 5. Let's see what we've got. There we go. There's our index, the ID, sequence structure, and whatnot. Cool. Let's see the train shape. See the test shape. Cool. So the test data set only has, let's just check. Here we go. So the test data set only has ID obviously, sequence structure, predicted loop type, sequence length, and sequence score. Okay. So let's see what the signal to noise distribution is. And we'll do that doing a histogram. And we'll put in the train, signal to noise, and we'll set the bins as 30, title, signal to noise dist. The width, let's set that as 1,000, so we get a good clear view, and the height, we'll set that to 500. Cool, and then fig.show should be fine. I've put too many there. There we go. Is it bin? It's bins, isn't it? Not bin. Going on value at LU. What have we got there? What have we done? Voila. So as we can see, the distribution is about, the signal to noise distribution is about from 0 to about 15. And as we can see here, we've used Plotly so we can check the counts and the signal to noise as well. Okay, that's cool. So what we're going to do now is basically look at the sequence length distribution and see what that is saying. However, what we'll do first is we'll remove the majority of the samples that, well, the majority of the samples lie between 0 and 6, and there are also negative values that we need to remove. So what we're going to do is query the data for the values which are less than or equal to 1. So train query to noise and equal to 1. Cool. It's fine. So let's look at the, as I said, let's look at the sequence length distribution. So we'll do the same again, but we'll just rob this code. No point in typing it out again. And it will be seq length, and the sequence, we'll change that to sequence length dist. Okay. There we go. So what we've got here, let's bin it a bit smaller. Actually, let's do 25. Let's just see if that makes it more clear. No, let's just bin it down to 10. Try that. And I know why. I should have changed the test. There we go. Silly me. So there we go. So we'll bin that up, bring them together a little bit. There we go. So we've got two distinct values here. Sequence length of 107, and there's a sequence length of 130. So it might be a good idea to split these two sequence, the data that, the 629 counts of 107 and the 3005 counts of sequence length 130. Let's split them. It might improve the overall performance of a model if we split the test data set based on the sequence length. So let's go public df, and we'll test query that, and it is the sequence length, and it's 107, and in the private df, let's test query sequence number 130, and that should split it fine. Okay, cool. Move on to the pre-processing. Okay, so what we're going to do now is create a dictionary with a character to integer layout, and that can be used to convert the RNA sequences, structure, and the predictive loop types into integers. So let's tokenize it. Token to integer, that's the variable we'll use. And it'll be x, I for I, x in numerate, and it will be then A, C, G, U, B, E, H, I, M. So I think that should be for it. And we'll take a look at that. Spelling's atrocious. There we go. Okay. What we're gonna have to do though now is build a function that converts a data frame to a 3D array. And we can use this to convert both the training features and the targets. So let's create a function. Data frame to array, and it'll take our data frame and it will return transpose MP array df values to list. Okay. And it'll be a 3D array, so it'll be 0, 2, 1. Okay. Voila. So the next step then is create a function that uses the dictionary we created here to convert training features into arrays containing integers. And what we'll do then is apply the data frame to array function to convert the data set into a 3D NumPy array, if that makes sense. So let's do data frame label coding. and it'll take the df, it'll take the token to integer, calls that it'll take, sequence, structure in the test set, predicted loop type. Let's highlight that like that. Okay. So what we're going to do, let's just make a note here. Tokenization of sequence, structure, and predicted loop. And it will return data frame to array. And it'll be the df, it'll be the calls that we specified. And we'll use the apply map and lambda function. And it will be token to integer for x in the sequence. I think we should be good on that. Let's just run it and see. Yep, seems to go ahead. Okay, now what we're going to do is apply these functions to the train data. So train inputs is going to be using the data label encoding, and it'll be train, it'll take the train and the dictionary that we made, the token int dictionary. Okay. Data frame. And then the train labels will be the data frame to array, and that will take train and the target columns. Okay. What have I done wrong there? Let's have a look. Okay, got you. I've missed a bracket. There we go. Let's just hit them again. Have I missed a bracket? That's 2 there. Delete that one. There we go. That should be fine. There we go. So let's rerun them. Voila. Okay. So what we've just done to the training set, we have what we've done. Well, sorry, what we've done with the test set, we split it into public and private categories depending on the sequence length. So now we're going to tokenize and reshape the test data set into a NumPy array using the data frame label encoding function. So public inputs rather, data frame label encoding. Okay. And it'll take the public df that we made earlier and also the token dictionary. Okay, and then the private inputs, we will do the same thing. Encoding, and it takes the private df and the tokenization dictionary. Okay, so we should be good to go on that. Happy days, it's worked. Right, that's our pre-processing done. Now, build model. Okay, first of all, before we get started, let's split the data. Okay, right, so we're going to have X train, X val, Y train, and we're going to have Y val. Train test split. We imported earlier from scikit-learn. It's going to take the train inputs, train labels, the test size. We'll set that to 10%. Random state is 42, and we're going to stratify train filter. That should be fine for our splitting. Okay. So what we're going to do is create the Monte Carlo root mean squared errors. That is a mouthful. And we're going to do that in the terms of a function. So let's call it MCRMSE. And that will take the true labels and it'll take the predicted as well. And we'll do the column-wise MSC TF reduce mean, and it'll be TF square, and that will be a calculation of the true minus the predicted, not equals, minus okay, axis 1. And what we wanted to return is the TF reduce mean, and it'll be the square of the col-wise MSE, mean squared error, axis 1 as well, because it's the columns. Okay. I think that should be good. Yep. Now, let's build the model. Let's just call it that. It's easy, isn't it? So it's going to take a number of different arguments, and these are subject. If you want to try and change these, change the numbers for these, it's absolutely fine. It's all about experimentation at the end of the day, but I'm just going to set them a certain way that I know that works. So embed size, that is the length of the unique tokens. Sequence length equals 107, and that will be the public dataset sequence length. We're going to take the pred length, and that is the predicted length for the public dataset, 68. We're going to put some dropout, and we'll set that to 0.5. That's one that you can mess around with. 0.5 is usually a good start and dropout figure. It's the default figure. We dropout, and we'll set that to 2. That's the spatial dropout. Again, play around with it. And then the embedded dimensions, we'll set that to 200. And the hidden dimensions, we'll set that to 6. That's the hidden layer units. Okay. So let's build the model. So inputs will be, we called the TensorFlow. What did we call L? L was the layer. So let's build the layer. Input shape. It will be the sequence len. Okay. Embed will be the L embedding, and that will be the input. The dimension will be the embed size that we mentioned in one of the arguments in the function. The output dim will be the embed dim. Cool. And then inputs will be there. Okay. We'll have to reshape it. And that will be using the TF reshape call, and it'll be embed shape equals -1 embed shape index X1 embed shape, embed dot shape index 2 times embed shape 3. Okay, fine. Let's do the hidden layer. That's where we'll do the spatial dropout. 1D we'll use, and that will be the SP dropout, and it will also be the reshape value. Okay, that's fine. So now we're going to use, let's just mark that, 3 bi-directional GRU layers. Okay, so I'll write the first one and we'll just copy and paste the rest of them. So it'll be L bi-directional and we'll use the GRU there. And I'll take the hidden dim dropout equals the dropout. Return sequence true, set that to true. Initialize the kernel to be auto. I can't even say that. There we go. Okay, so let's now copy and paste this. 3 layers of the same thing. Well, let's just move that slightly there. Okay. Copy and paste that. Yeah, and we should be good to go on that one. Okay. We'll check that sequence. Yeah, okay, that's fine. That's why, because I've called that length, it should be len. There we go. Okay. Right. So we're going to make the predictions on the first part of each sequence. So we have to truncate it. And how we do that is set a variable, hidden, and that will be, we'll truncate that. Pred len, isn't it? Yeah. Okay. And what we want out is the dense layer 5. Activation, we'll set that as linear, and it will also be truncated. Okay. If I put pred length, I have, haven't I? So typing as we're talking, that should be fine. There we go. The model TF Keras model inputs will be inputs, and outputs will be outputs. And then we will compile model. The optimizer we will use will be Adam, good one to go to, and the loss will be the function we defined before. There we go. And the loss function, let's call that, let's say what that is again. The Monte Carlo root mean squared error. It's a mouthful. Okay, and then the last part is return model. Boom. So the default parameters of our model are the sequence length is 107. The prediction length is 68. The dropout is 0.5. The spatial dropout is 0.2. The embedded dimension is 200 and the hidden layers dimensions is 256. Okay, so let's run that. Happy days. No errors, despite my spelling. Okay. So what we're going to do now is apply the tokenizer to the model build function. And we'll do that by setting model as build model embed size equals the length of the dictionary that we made, the tokenizer. Okay, so that will be 14. It'll be build model, sorry. Okay. Fine, and then we'll get the model summary and see what we're working with. Oh, have I just spelled that wrong? I think I have, haven't I? What have I spelled wrong? Initializer author. What have I done wrong here? Yep, I spelled it wrong. There's an I there. I don't know why I didn't. Don't know what's going on, but there we go. Spelling mistakes. Oh, it's Kane. See, it's Kernel. Kernel. There we go. That should be fine now. There we go. So what we're going to do, we've got a model, and the total trainable params nearly 3.7 million. So we're going to train the model for 40 epochs, and the model checkpoint will be saved in a model folder. We're going to set the batch size to 64. I've run this model before, and 64 was probably the best result. Feel free to experiment 16, 32, 64, and so on and so forth. 64, though, as I said, I've experimented before, and it generated superior results, and it had quite a quick convergence as well. So let's do that. Okay, let's go. So if model train, remember we set that to true earlier on, equals model dot fit, and what we'll fit is X train, Y train, validation data. That is our X val and our Y val. Batch size equals 64. The epochs equals 40. Experiment with that as well. Verbose is 2, so we get some information out of it. And the callbacks, let's set a call. Okay. Harass callbacks, and we will call back the reduce LRONP plateau. Fill it in, yes, the plateau, and we'll set the patience to 5, and we'll also set tf harass callbacks, and as we said, the model checkpoint, and we'll save that in model H5, so it'll save every time. Cool. Did I do that right? Should be right, shouldn't it? I think that should be okay. We'll give it a go. There we go. So what I'm going to do is pause this video, and once it's trained, it can take between about 20 minutes to half an hour. We will come back and we will basically evaluate our model, check the results, and take a look. Okay, hopefully you've trained the model. Didn't take too much time. So what we're going to do is check the results, and we're going to plot our loss and validation loss. Again, if model train, we will use a line plot, and what we'll be plotting is the history dot history. The y-axis will be loss and the val loss. The labels, they will be the index, epoch, the value, and our loss function, which is MCRMSE. And of course, we'll give it a title, and it'll be called history. Okay. Cool. And then fig show. Yeah. There we go. So both the validation and the training loss were reduced up until around, shall we say, 35 epochs, and then it sort of flat lines in a way. So what we should do is test results on both 22 and 35 epochs. Since the test data set was split into public and private sets with the various sequence lengths, 107 and 130, we can build two distinct models and load our previously saved checkpoints in order to predict the degradation on the various lengths. RNN models can take input as sequences at different lengths, so this is quite conceivable to do. Two unique models with different sequences and prediction lengths will be then developed. So while our private model contains 130 sequence lengths, our public model only has 107. So to forecast the degradation of mRNA, both the models will need to be loaded with the weights that we saved. So we'll do that now. So model public, call the build model function, sequence length. This one will be 107. The pred length, 107. The embed size, we will have len token int dictionary. Model, not models. Okay, and then we've got the model private. We'll pretty much do the same again. Let's just copy and paste that. But that will be 130. 130, and we'll leave the embed size. Okay, so model public, and what we want to do is use the load weights, and that will be stored in model h.h5. I've hit that prematurely. Let's just interrupt that execution, and then we'll do the same. Private load weights. Okay, so let's run that. Give that a moment. Okay, now we can build a prediction using this model. So public preds equals the model public dot predict, and then public inputs. We'll do the same for the private. We'll change that to private predictions model private, and also private inputs. Oh, I've wrote that wrong again. Let's just interrupt that. Let's just check shape. Private threads shape. Okay, run that. That took a couple of minutes to run. So the output, as you can see, we've got a 3D NumPy array. And what we need to do to make any sort of sense of it is to make it into a data frame. So what we're going to do is combine both the private and public data frames. We'll add a series of integers in front of the ID based on a sequence of single predictions, and then concatenating all the data into a pandas data frame, and we can prepare that for a Kaggle submission if we wish. So what we're going to do is make a empty list, and then we'll do a for loop. df threads in, make a list here. So we need the public df, the public threads, and then the private df and the private threads, and both of them are contained within a tuple. Okay. And then for I, the ID in enumerate df.id, single prediction will be preds I, and then the single df will be pd data frame, single pred columns will be our target cols. If I remember correctly, that's what we called them. And then single df ID C. Yeah, okay. And this is where we'll add a series of integers in front of the ID based on the sequence of single predictions. So we will need an f string, and it will contain the UID, x like that, for x in range single df dot shape. So, and I think that would be good. And then finally, threads, and let's append the single df to the list. Okay. And then final step is the sorry, that'll be pred, won't it? Okay. Preds df. That will be the concatenation of preds pred ls. I hope that will work. So let's just put the pred. Oh, don't want a markup. I want a code cell. Thank you very much. df.head. We'll take a look at that once it's run. Okay, take a look. There we go. So what we can see is that we've got the ID, the sequence, and the prediction there as well. So that was pretty good, pretty easy and simple to set up. Now this was a Kaggle competition. So if you would like to submit this to the Kaggle page, we can do that now, and I'll show you how to do that. So what we need to do make a submission file. And we will do that by taking the ID and predictions. And what we want to do is merge that to the creds.df on ID seq POS, and then submission to CSV to make that a CSV file. /submission, and we'll get rid of the index, false, and then submission. We'll take a look at that. And there we have it. That is the Kaggle submission as the sample submission dictates. And that is it. That is a small project on the degradation of mRNA molecules using the Stanford COVID vaccine dataset, which has been pulled from Kaggle. I've hoped you have understood what's been going on. If there's any questions, please pop them into the comments on this video. And I hope you are looking forward to the next code along. Thank you very much.